Alright, so we've seen what happens when they give us an equation and we have to draw a graph from it. That's not too bad. We can also go the other way. They can give us a sketch and say, figure out what equation this must have come from. If we're speaking standard form, then our quadratics look like this. Now, I actually learned this with H and K. Sometimes they teach it with P and Q. It doesn't matter all that much. The point is that there are two parameters here. This one determines how far you've moved to the left or right. This determines how far you've moved up or down. And A, this one's pretty consistently A, is your vertical stretch factor. And if it's negative, it tells you that your parabola is upside down. In this case, you can pick off P and Q very quickly because they've told us where the vertex is. The vertex is minus 1, 2. These are P and Q. So, just like that, we know our curve must look like x plus 1 all squared plus 2. Maybe you're saying, wait a minute, this is a negative 1, why did you put plus 1? The formula says you have to put a negative in front of that number. So think of this as x minus negative 1. Or the other way to remember it is simply that horizontal translations are annoying and backwards, whatever works for you. So this is good. We've got two parameters down just like that with hardly any math so far. The other thing we know is they tell us our curve has to go through negative 3, 1. In other words, when x is negative 3, y has to come out to 1. Okay, that can be arranged. We'll write this again and plug those values in. Y equals a times x plus 1 all squared plus 2. I'm just plugging in the values negative 3 and 1. Now that we've done that, a is the only variable left, which means we should be able to corner it and solve for it. Let's see, we get a times negative 3 plus 1 is negative 2. Negative 2 squared is 4. Subtract 2 from each side to get rid of this, and you get negative 1 equals 4a. Divide by 4, and you get a is minus 1/4. It makes sense that it's negative because we can see our parabola is supposed to open down. The 1/4 means it's relatively flat compared to a normal parabola, which is shaped more like this. So I'll just write it out one last time. Our standard form is, I know what a is now, it's minus 1/4, and then we just copy out all the other stuff we had. X plus 1 all squared plus 2. So there's our standard form. Now, find algebraically the intercepts of the graph. You remember how that works? To find x-intercepts, you plug in y equals 0. To plug in y-intercepts, you set x equal to 0. I'm going to do the y-intercept first because it's easier. We'll need a little more time to grapple with this. So if x is 0, we get y equals minus 1/4 x plus 1 squared plus 2. 0 plus 1 is 1, squared is 1. That felt like a bit of a waste of time, but oh well. Minus 1/4 times 1 is minus 1/4, plus 2 is 7/4. I skipped through this because we're supposed to be amazing at fractions by now. If you're not totally confident about this, grab some scrap and convince yourself that when you do the common denominator here, you get minus 1/4 plus 8/4. It really does make 7/4. For the x-intercepts, we have to put y equals 0, which means a 0 goes in right here. So we get 0 equals minus 1/4 x plus 1 all squared plus 2. Subtract 2 from each side. So we're solving this for x. Okay. You can get rid of this minus 1/4 a couple of different ways. You can divide by minus 1/4, which means dividing by a fraction, which is not a pleasant experience. Or the easier way is to multiply by negative 4. I prefer that way. If you do that, These negatives cancel out, these 4's cancel out, the fraction's gone. That's what we really wanted. On the left side we get 8, and now it equals x plus 1 all squared. Square root both sides to strip off the square, and you get x plus 1 equals, now I'm about to forget something. Do you see what it is? There's something small but pretty important missing from what I just wrote. Right here, we need plus or minus. Every number other than 0 has two different square roots, a positive version and then a negative version. So that gets us most of the way. Now we take this 1 over to the right-hand side, and you get x equals negative 1 plus or minus the square root of 8. Now, I just note, exact values is what we have right now. These are considered exact values because if you wanted this to a billion digits, in theory you could work it out. The nearest hundredth version we're going to have to pull out the calculator to work out. Let's see, 7 over 4 is 1.75. To do that on the calculator, you just do 7 divided by 4 and out it comes. To get these, the two x-intercepts, we have to do negative 1 plus the square root of 8, and then negative 1 minus the square root of 8. You just run this entire calculation once with the plus and once with the minus. So negative 1 plus root 8 makes 1.83. And negative 1 minus the square root of 8 gives minus 3.83. Good so far. Now, domain, range, and equation of the axis of symmetry. For any quadratic, whether it opens up or down, the domain is a complete pushover. It's always the same thing. Turn off your brain for a moment and write XER. That's it. Because these extend forever to the left and forever to the right, they're defined for every real number. Nothing to it. The range is a little different, though, because while up here, this thing may go down forever, it doesn't go up forever. It goes up to, there's 0, there's 1, 2, right here at the vertex, is the highest this thing ever gets. It's always 2 or something lower than 2. So for the range, you can say y can be any real number, comma, y is always less than or at least equal to 2. Your teacher may not care about this YER part. Some of them feel it isn't necessary as long as you have the y less than or equal to 2. I was taught to always put this in, but not a huge deal. This is the part that they really want to see, that you noticed 2 is the highest y value this can ever reach. And the axis of symmetry is a line that cuts this right in the middle into two mirror image pieces. Because it's a vertical line, the axis of symmetry will always have an equation that looks like x equals something. In this case, well, it's got to go through the vertex, right? So if the vertex is at negative 1, 2, if you want to hit that, then x better equal negative 1. That's the equation of the axis of symmetry. If you want, you can take this negative 1 over to the left and get the equation x plus 1 equals 0. I've never liked that form, but you see it in solution manuals sometimes, and there's technically nothing wrong with it. So, domain XER, pretty much always range. Depends on whether you have a maximum or a minimum. In this case, 2 is the highest we ever get. So we say y is always lower than or equal to 2. And the axis of symmetry is a vertical line that cuts through the vertex.